Okay, so we've taken two videos now and we've discussed kind of the point leading up to analyzing the mixture, but we really haven't gotten there yet. So we need to take a look at maybe some of the things that we've talked about before and just kind of wrap it all up nice and simple up here at the top. So we said that we are analyzing a mixture, and this has a first component of aspirin, and it has a second component, which is caffeine. And we have just made some standards, and we've analyzed the standards of each one, and we calculated the real molar absorptivity of each one of these. So we said that aspirin had a lambda max of 229. So lambda max of 229 on our spec. And we said that caffeine had a lambda max of 272 on our spec. So I'll write those numbers down. And we used the absorbance and the concentration that we made to calculate a molar absorptivity. So the molar absorptivity of my aspirin, we calculated at 866, and the molar absorptivity of my caffeine, we calculated at 8042. Okay, so that's kind of the point that we've led up to now. And we talked about this is a mixture, so we're going to have to cross-reference the two solutions, right? So I've analyzed aspirin at the aspirin settings, and I've analyzed caffeine at the caffeine settings. And now step number 3 that we need to talk about is you're going to cross-reference the two solutions. You did the same thing with the chrome and manganese mixture. You made a chrome and analyzed it at chrome. You made a manganese and analyzed it at manganese. And then you took the two and you analyzed them at each other settings, meaning you took chromium and analyzed it at manganese settings. And you took manganese and you analyzed it at chrome settings. So the same thing's going to have to happen here. We're going to take aspirin and we're going to analyze it at caffeine settings. We're going to take caffeine and analyze it at the aspirin settings. Okay, so what does that mean? All right, so let's take a look. We're going to take aspirin first. And aspirin, we know, has a molar absorptivity of 866, but that is at 229. Okay, so the molar absorptivity is 866. Well, there's another component in here, and that component is caffeine, and caffeine is absorbing at 272. So we need to know what is the molar absorptivity of aspirin at the 272 number. If these are the two wavelengths that I'm going to be analyzing, then I know that aspirin is going to be majorly absorbing at the 229 region. And I know that caffeine's going to be majorly absorbing in the 272 region. But you know, aspirin's going to be absorbing in 272 as well. It might not be the lambda max, but it's going to contribute to some of the absorbance. The same thing's going to happen to caffeine. Caffeine majorly absorbs at 272, but you know, caffeine is in there, it's in the mixture, and even at 229, which is the aspirin number that we're using, we're going to see some absorbance with caffeine. So I just want to make sure that I understand that the absorbances at each one of these wavelengths are really contributing to both of these components. And that means that not only do I have to analyze aspirin at aspirin's wavelength, but I'm going to have to analyze aspirin at the caffeine wavelength as well. I need the molar absorptivity for that number too at 272. Caffeine, same discussion here. Caffeine is at 272, and I just calculated the molar absorptivity. That was 8,042. But you know, caffeine's in the sample. It's in that mixture. And caffeine does give me an absorbance at 229, which is aspirin's wavelength. But caffeine can contribute to some of that absorbance. So I'm going to have to calculate the molar absorptivity of caffeine at aspirin's wavelength. Right? So this is what we mean by cross-referencing. Analyze aspirin at aspirin wavelength. But you also need to analyze aspirin at the other component's wavelength, and in this case it's caffeine. The same thing's going to hold true for caffeine. Analyze caffeine at caffeine's wavelength. And then you're going to analyze caffeine at the other component's wavelength. And that other component is aspirin. Okay, so I take my standard. That's what I do. I take my aspirin standard, and then I put it on the spec, and I get this typical curve. Here's the lambda max, basically, for aspirin. We already talked about that number. And 272 is kind of down in here somewhere. Right? And then I do the same thing for the caffeine. I put caffeine on the spec, and I analyze it, and I get something that maybe looks like this. This is the lambda max for caffeine. And 229, probably somewhere down in here. And that number I need to focus on. Okay, so how do we do this? How do we calculate the molar absorptivity of these numbers? Well, depending on the spec that you're using, you can click, basically, for aspirin, you can click 272 and it will give you an absorbance here. And that absorbance I'll write down. Or you can do a go-to feature. And you type into the machine, basically, I need you to go to 272 nanometers, and I need you to give me an absorbance. So what begins to happen here is that I put my aspirin standard in the UV-Vis. I go to 272 nanometers, and at 272 nanometers, I might get 0.034 absorbance. Really low, right? And look at it. It is probably going to be low. That is not my lambda max. Aspirin is going to be absorbing slightly in that region, but it shouldn't be absorbing that much. It might not, and in this case it's not. Okay, so I get an absorbance for aspirin at 272. Okay, so at this point, I'm trying to calculate a molar absorptivity at 272. Okay, well, if I need to calculate molar absorptivity, that's Beer's law. I just found out the absorbance of my aspirin standard, 0.034. I need to calculate the molar absorptivity, so that stands as E. B is the path length of 1, and C is the concentration that I made. And the concentration that I made of this standard, again, was 7.76 times 10 to the negative 4th. So to calculate for molar absorptivity, I take 0.034 and I divide it by 7.76 times 10 to the negative 4th. And when I do that, my calculated molar absorptivity is going to be 44. Now this is the molar absorptivity at the caffeine wave number or wavelength. All right, so much lower. And again, it should be. All right, I do the same thing for caffeine. I take my caffeine standard, I do a go-to feature, and I'm going to type in aspirin's wavelength, not caffeine's, but aspirin's, right? I'm trying to get the molar absorptivity at 229, so 229. And when I do that, it's going to give me an absorbance. And let's say that this absorbance that it gives me is 0.073. Okay, so I know caffeine absorbs really here at this location, but you know, it's going to give me some absorbance down here too, and I just have to figure out how much, and that's what this is doing. It's telling me how much absorbance is due to caffeine at the aspirin wavelength. So again, I need to figure out the molar absorptivity at that number. So A equals EBC. The absorbance is 0.073. Molar absorptivity I'm trying to calculate, path length is 1, and the caffeine standard that I made was 1.17 times 10 to the negative 4th. So in order to solve for molar absorptivity, I take 0.073 and I divide it by 1.17 times 10 to the negative 4th, and the molar absorptivity that I get here is 624. So this is the molar absorptivity for caffeine at the aspirin wavelength. Okay, so these are just bits and pieces of the information, and we haven't really even talked about analyzing a mixture yet. This is just analyzing the standards. That's all that we have done. And again, you did the same thing when you did the chromium manganese mixture. The exact same procedure. So we've made a sample of aspirin and we've made a sample of caffeine. We ran aspirin at the aspirin settings and got a molar absorptivity. We ran aspirin at the caffeine settings and got a molar absorptivity. And then we did the same thing to caffeine. We analyzed caffeine on the machine at caffeine settings. Then we analyzed caffeine at the aspirin settings. And now we've got 4 molar absorptivities, and we can use those molar absorptivities in the matrix equation when we begin to analyze our mixture. So in part 4 of this video lecture series about the matrix problem, we will finally talk about the actual mix and analyzing that mixture and putting together all of this information. So again, stay tuned. We've got another video or two that's coming your way.